Okay, it's filming.
Okay. Hello and welcome to your latest episode of Carbon Cuties. Ever wonder how organic nomenclature works for alkanes, alkenes, and alkynes? Well, you're in luck because today your very own Carbon Cuties are going to help you out. First, let's introduce today's exciting topic, organic chemistry.
Organic chemistry is the study of carbon and its compounds, called organic molecules. Organic compounds form into several different compounds we know today, such as diamond, coal, sugars, fats, and many more. Even the perfume you put on in the morning, composed of ethanol, is made up of an organic compound. Carbon compounds are made up of two parts: a saturated carbon, which is the skeleton of the compound, which is the backbone of the carbons linked by the single bonds attached solely to hydrogen atoms. This part of the compound is typically unreactive, whereas the reactive part of the compound, the second component to the organic compound, is called the functional group. We'll talk more about functional groups later on. You probably know quite a few names for organic compounds, but you probably didn't know how these names came about. There's a whole history that comes with the naming of organic compounds, but before we get into that, let's learn about the basic naming of organic compounds. In order to name the increasing number of organic compounds that arise each day, systematic nomenclature systems have been developed to identify each and every different compound from one another due to their structural formula. These two naming systems were called the common naming system and the IUPAC naming system. First type of naming is the common, trivial naming. The common names here each have their origin in the history of science and natural sources. However, these names are quite arbitrary, and there is no step-by-step process on how to name them. No rational or systematic principles underlie the common naming system. Here are a few examples of compounds named within this system. We have methane, with the formula CH4, butane, C4H10, acetone, CH3COCH3, and toluene, CH3C6H5. The second type of naming is IUPAC naming. As we've mentioned before, organic chemistry is based off of carbon bonding in the characteristic lattice of chains and rings. It is necessary, therefore, for it to have a naming system that indicates how many and how these carbon atoms are bonded together. This system should also identify any functional groups present in the compound. IUPAC naming was created in order to solve the problems that arose from the arbitrary common naming system. Knowing the rules of IUPAC naming system and being given the structural formula, you will be able to name every distinct compound that there is. And when given the name of a compound in IUPAC, you will be able to write a structural formula. There are three components to the IUPAC naming system. The first, a root or base indicating a major chain of rings or of carbon atoms found in the molecular structure. Second, a suffix of other elements designating functional groups that may be present in the compound. And the third, names of substituent groups, other than hydrogen, that complete the molecular structure.
Alkanes are a homologous series of saturated hydrocarbons, so they do not have a functional group. They are unreactive and nonpolar. They have the general formula CnH2n plus 2. For example, methane has 1 carbon and 4 hydrogens, CH4. Alkanes have sigma bonds and are sp3 hybridized, so carbon-carbon single bonds only.
The first step to naming alkanes begins by counting the carbon backbone. The backbone is the longest unbranched chain of carbons in the molecule. Take, for example, this hydrocarbon. The backbone is made up of 5 carbons. The number of carbon refers to a predetermined name which will become the suffix of the alkane name. These names are shown in this table, where 1 carbon is methane, 2 ethane, 3 pentane, and so on. Thus, the suffix for this hydrocarbon is pent, and since it's an alkane, it ends in ane, thus making this compound pentane. Wasn't that easy? Now let's make it a bit more complicated. Let's take a look at this compound. As you can see, it is similar to the last one we looked at. It also has a 5-carbon backbone, meaning it is pentane. However, there is a substituent. To name this compound is simple. First, you must determine the backbone, as we have already done. Next, you must number the chain. The key to remember here is that the substituent must fall in the lowest possible number. so I could number this from left to right or right to left. However, the correct way would be from right to left, since the substituent would fall on the second carbon. Now you must name the substituent, which will become the prefix for your alkane name. In this case, it is one carbon, and by referring to the same table, we know to name it methyl. When naming substituents, there are two things you must be sure to include: the locant of the substituent and how many there are. The location can be indicated by a number, and how many can be indicated by using Greek prefixes, mono, di, tri, etc. Thus, in this case, the alkane is called 2-methylpentane. Sometimes it is not necessary to indicate the locant. Take, for example, this alkane. There's a 3-carbon backbone, so it is propane. But since there are only 3 carbons, there's only one possible location for the substituent. Thus, it is redundant to put the number. Here's another example. With 2 methyls on the center carbon, this carbon would thus be called dimethylpropane. To practice even more, let's look at a few examples using line diagrams.
A line diagram, also called the skeletal formula, is a shorthand version of representing the bonds between hydrogen and carbon in organic chemistry. It also provides information about the molecular geometry, VSEPR, of the molecule, in a 2-dimensional representation. Line diagrams are pretty straightforward. First, you need to find the carbon backbone. Your line diagram will consist of this and possibly a functional group contained within the molecule. Since it is so common for a hydrogen atom to be bonded to carbon, we omit this bond from our line diagram for clarity and compactness, as well as the fact that it is easily identifiable whether a carbon is attached to any hydrogen, valence electrons. Take a look at the line diagram for butane, for example. The chemical formula for butane is C4H10. Butane's line diagram looks like this and represents all the carbon-carbon bonds of the molecule, but we don't need to add lines for H atoms, as we can deduce how many hydrogens are attached, knowing how many carbons one carbon is attached to. If, however, there is a functional group that does not fall in the category of a carbon-hydrogen bond, it is specified. Here's an example.
That was so much new information. You guys must be saturated. Now let's talk about unsaturated hydrocarbons like alkenes.
Okay, time for your beloved carbon cuties to investigate alkenes. Alkenes are homologous series of unsaturated hydrocarbons with multiple carbon-carbon double bonds. Their general formula is CnH2n. The 2 carbon atoms in alkenes are sp2 hybridized with a pi bond and a sigma bond and have trigonal planar geometry around each carbon. Unlike alkanes, alkenes do have a functional group, the carbon-carbon double bond, so they are reactive. However, there is no free rotation with double bonds as with the single bonds in alkanes because of the presence of pi bonds. It is important to note that alkenes can form isomers with different positioning of the double bonds, cis-trans isomers and chain-branching isomers, which is essential for the nomenclature process. Look at this compound, for example. The longest chain has 3 carbons, and there is a double bond, so we know it's a propene. Now we have to identify where the double bond is, in this case on the second carbon. The location of the double bond, 2, is indicated between the prefix, prop, indicating the presence of 3 carbons, and the suffix, -ene, indicating the presence of a double bond, giving prop2-ene. Now, let's look at an example with a substituent attached. Lowest numbering must always be given to the double bond. Here, we have a longest chain of 5 carbon bonds with a double bond on the second carbon, and an ethyl group attached to the third carbon. Take a moment to think. Did you get it? The answer is 3-ethylpent2-ene. Let's try one more. 4,4-diethyl-hex-3-ene is correct. Now, let's add the complexity of cis and trans isomers. If 2 groups attached to the carbons of a double bond are on the same side of the double bond, it's a cis alkene. If the 2 groups lie on opposite sides of the double bond, it is a trans alkene. Consider this example. There are 2 carbons attached via a double bond, as well as 2 chlorines attached on the same side of the double bonds. Using Greek prefixes, we must indicate the number of chlorines attached, as well as the location of each chlorine. Therefore, the compound is cis-1,2-dichloroethene. What about this one? The CH3 groups are attached on opposite sides of the double bond, forming a longest chain of 4 carbons. We call this compound trans-but-2-ene. Now you know everything there is to know about alkenes. The carbon cuties have taught you well.
By now we've talked about single and double bonds, but what about triple bonds? Alkynes, formerly known as acetylene, are the functional group of hydrocarbons with at least one triple bond. Their general formula is CnH2n-2. Alkynes are also unsaturated, have a linear or straight geometry, and are simply sp hybridized with a sigma bond and 2 pi bonds. Because of these pi bonds, alkynes do not have free rotation. Like other hydrocarbons, alkynes are generally hydrophobic and tend to be more reactive. Now let's try naming some alkynes. The IUPAC naming for alkynes is very similar to alkenes, except instead of the suffix -ene, when there are 3 bonds, we use the suffix -ine. Here are some examples. By counting the longest carbon backbone, we know that this is butyne. The triple bond is on the first carbon, so it's but1-ine, and there's a methyl group on the third carbon, so the final answer is 3-methyl-but1-ine. What about this one? Using the same method, we know that this is 3,3 dimethyl hex 4-ine. And finally, let's try an example of a line drawing. This one is 5-ethyl hep 2-ine.
Wow, cuties! All that stress about organic chemistry just got lifted off your shoulders, didn't it? We learned about alkanes, alkenes, alkynes, and we learned the step-by-step processes of how to name compounds in the common naming system and the more efficient IUPAC naming system. Hope you had a great time on Carbon Cuties!